Welcome to this lecture. In this week, we are looking at limiting behavior of measured theoretic integration. One of the major results that we have seen has been the monotone convergence theorem, which was a property involving this limiting behavior of measurable functions and corresponding limiting behavior of the integrals. Alright. But we have also seen that as a consequence of monotone convergence theorem, we had the additivity property. Now, we are going to discuss further general results that apply in limiting behaviors. Okay. So, let's move ahead to the slides and discuss. Alright. So, we have already seen this monotone convergence theorem and seen these useful applications. We are now focusing towards results specifically involving limits of these integrals. Now, an important comment is that in all of our discussion we are going to fix this measure space omega, script f and mu. Alright. Now, here is a very important result that's called the Fatou's lemma, and this is applicable to quite a general situation, and that is why this has been referred to as theorem, even though it's called as the Fatou's lemma. Alright. So let's consider this situation that you are looking at this Bodel measurable functions f1, f2, fn, so on, that's a sequence, and then you consider a function f. So these are some collection of Bodel measurable functions. Now, if it so happens that fn's, the functions, are dominated from below by this function f for all n, and if the integration of f is avoiding the value minus infinity. So first of all, integration of f should exist and avoid the value minus infinity. In this situation, you can get a statement involving integration and limit inferior of the sequence of functions. Okay, and this says that you can bring out the limit inferior from the integral, but you will end up with an inequality. Okay. So therefore, integration of limit inferior of functions is less or equal to limit inferior of the integrations. Okay. So this is the first part of the statement. The second part says that if you have a bound going in the other direction, so that means that if fn's are dominated from above by this function f, and if it so happens that the integration of f exists and avoiding the value plus infinity, then you claim the other sided inequalities, but it involves limit superior of the functions and their integrations. Okay. So here the statement says that integration of the limit superiors is at least limit superior of the integrations. Okay. So that is the statement here. You might recall that a similar statement was considered for the extended version of the monotone convergence theorem, right? So therefore, we have seen such lower bounds given by a certain type of a function, and we had considered the limiting behaviors. But here it's important that the sequence of functions in the extended version of the monotone convergence theorem should be monotone, meaning either it should be increasing or decreasing. Okay. But here in Fatou's lemma, we are not assuming any monotone behavior of the sequence of the functions. Okay. And as such, it's important to note that limit of the functions, pointwise limit of the functions, need not exist. Okay. However, what we can always talk about are these functions limit superior of the sequence and limit inferior of the sequence. These are the things that are appearing in the statement of the Fatou's lemma. Okay. Alright. So how do you prove this Fatou's lemma? So consider this sequence of functions fn, and using this sequence of functions, consider another sequence of functions, call it gn. So how these gns are defined? So you look at, for integers n, 1, 2, 3, 4, so on, you look at the infimum of the remaining functions. So that means that if your n is 10, look at f10, f11 and so on. Look at all those functions, look at the infimum of that. Okay. So pointwise infimum will define for you the corresponding function gn. Okay. So that's how these functions are defined. Alright. But then remember, infimum over a countable set of functions. If the functions fn's are given to be Bodel measurable, then you immediately get the functions gn to be measurable. So infimum will give you measurable functions. But moreover, there are certain interesting properties of this function gn. So here f case, when you are considering the monotone behavior, here the infimums are always less equals to the individual fn, right? So gn's are less equals to fn by definition. But you have also assumed here in the first part that fn's have a lower bound given by the function f, okay? But now you also have that the gn's are increasing in n and it will approximate the limit inferior of the functions fn, okay? So here this is an important comment that this infimum of the functions, that's how the gn's are defined, they increase in n and increase to the limit inferior of the functions. Now here what you do, you have constructed a sequence of functions gn which are now monotone increasing, and are bounded from below a function f with integration of f avoiding the value minus infinity, right? So therefore you can apply the extended form of the monotone convergence theorem and you immediately get that integrations of gn will increase and increase to the integration of limit inferior of the functions fk, okay? So that's a statement here that applies from the extended form of the monotone convergence theorem. Now you would like to make this connection with the actual sequence of functions fn's and their integrals, right? So let's just try to compare the integrations of gn and integrations of fn. So you want to bring in fn now and you want to connect it with the integration of the limit inferior, which appears as the limit of these integrations of gn's. Alright. Now for every fixed n you have this inequality because gn's are less equals to fn's. Now you observe this set of arguments that integrations of limit inferior of the functions fk will be equal to limit of integrations of gn, that's already observed. Limit of integrations of gn, that will be equal to limit inferior of the integrations of gn. Why? Because the limit exists here, so therefore it's equal to the limit inferior. So that's all we are using. But now observe that individually gn's integrations of that is less equal to integrations of fn's, right? So therefore limit inferior of integrations of gn will be less equal to limit inferior of integrations of fn, and therefore you get the required inequality that integrations of limit inferiors of the functions is less equal to limit inferior of the integrations of the functions, okay? You get the inequality, okay, required inequality. This proves the part 1, okay? But now from part 1 you can prove part 2 by observing that limit superior of the functions and limit inferior of the functions have this interesting connection that limit superior of the functions is equal to minus of the limit inferior of minus fn's, right? So now let's go back to that assumption in part 2. So you are going to consider the minus fn's now. So if you consider the minus fn's, you immediately get the lower bound given by minus f, and for minus f the integration of that avoids the value minus infinity, right? So that's exactly in the setup of part 1, and therefore you can consider limit inferior of the minus fn's, and therefore by part 1 you get limit inferior of the minus fn's is less equal to limit inferior of the minus of integrations of fn, and just multiply both sides by minus 1, you will immediately get the required relation involving lim sup as stated in part 2. So the proof of Fatou's lemma is pretty simple as long as you choose the right function, the right sequence of functions, and you will immediately get it. Alright, so therefore that proves Fatou's lemma. But it's important to note that in part 1 of Fatou's lemma, if all the functions are non-negative, then we may as well take the lower bound function to be identically 0. So this is used sometime. So you are having this general form of monotone convergence theorem now, that if all the functions are non-negative, even though the functions are not converging to a limit, you can consider limit inferior of the functions and limit superior of the functions, and you can claim certain inequalities involving the integrations of the limit inferior and limit superior. Alright, now in the Fatou's lemma you have observed that we have only managed to prove an inequality, right? So you might ask whether we can actually improve it to an equality. So it so happens that you will actually get a inequality. You cannot improve it further. So we are showing this by an example of a strict inequality that might appear. So you cannot get an equality statement. So consider the Lebesgue measure lambda on the real line and consider a sequence of functions fn. So again, the setup of Fatou's lemma, you don't expect these functions to be monotone, but you should expect to get some kind of a limit inferior or limit superior. So let's try to look at this kind of functions given by n times indicator of open 0 to closed 1 by n. So these functions takes the value n on the interval open 0 to closed 1 over n. Everywhere else this function takes the value 0. Okay, so that's how the functions are defined. Now it's easy to check that the limit function actually exists here, and therefore the limit inferior will agree with that limit function. So here for any point x you can show that the limit function is identically 0. Okay, so therefore integration of the limit inferior of the functions is exactly 0. So if you integrate this limit inferior with respect to the Lebesgue measure, limit inferior is identically 0, so therefore the integration is identically 0. Great. But what happens to limit inferior of the integrals? So let's first compute the integrals of fn's. So here fn's, remember, they are n times the indicator of the interval open 0 to closed 1 over n. So therefore follow the definition of the integral with respect to the measure lambda, the Lebesgue measure, that will be nothing but n times the Lebesgue measure of the interval open 0 to closed 1 over n. But that is nothing but n times 1 over n, which is 1. So for all positive integers n, you immediately computed that the integrations of fn is exactly equal to 1. So therefore limit inferior of the integrations of fn is exactly equal to 1. Here you are getting a strict inequality that integrations of limit inferior of fn's is exactly equal to 0, but limit inferior of the integrations is equal to 1. So this is a strict inequality. So therefore you cannot improve the Fatou's lemma statement further and put it as a equality. You cannot do that. And now we go to a more general result, and this is a very important result in measure theoretic integration. This is called the dominated convergence theorem. So again, we are now going to consider limit functions and their integrations. Okay, so all right, so and this is going to give us some ideas on computing integrations by approximations. So here we are considering a sequence of functions f1, f2, so on, and consider a function f. So suppose that sequence of functions converge to f almost everywhere. So see, we have now relaxed the convergence to involve this almost everywhere statement. So what does it mean? So we mean that there exists a mu null set n such that outside the mu null set, on the complement of the mu null set, the convergence holds and the function values fn will converge to the function value of f. Okay, so for all those points outside the null set, you will get the convergence. So we don't care what happens on the null set, because we have already remarked that values on a null set will not affect the integrals values. Alright, so we are here interested in the integrations values. So if it so happens that the functions, the original functions, are dominated by a fixed function g, this is very important. You need a fixed function g that dominates mod of fn. If it so happens for all n, and if g is integrable, then you claim that the limit function f is also integrable, and you get this exchange of limit and integration. So by that I mean integration of f d mu is, which is exactly equal to integration of limit fn's is equal to limit of integrations of fn. Okay, so you are allowed to exchange the order of limit and integration here, and that will agree with the integration of the limit function, even though it is a almost everywhere convergence. Alright, so again remember here the first equality immediately follows because these two functions agree almost everywhere. Okay, only on a null set these functions might differ, but it doesn't affect the values of the integral. Now as per the conditions, fn's are dominated by a integrable function g, and therefore fn's are already integrable, so that's not an issue. So but here you need to show that integration of f that is well defined, and in particular you are claiming as a part of the statement of the theorem that f is integrable. So you have to somehow establish that. So how do you prove this? So start with this bound that is given to you. Okay, Alright, so now these functions mod fn, they are non-negative functions, right, and they are dominated from above by this integrable function g. Now here you get the pointwise convergence of fn's to f, right. So therefore you get that mod of f is dominated from above by this function g almost everywhere. Outside this null set where possibly the convergence does not hold, so on the null set the possibly the convergence may not occur. So outside that null set you get this pointwise convergence, so therefore you get this bound, upper bound given by the function g. Now you consider a different function g tilde, which we are going to use as a upper bound from the function mod f. So look at this function g tilde. So on the situation, on the points where mod of f is dominated by the g function, there you retain the function value of g, otherwise you assign the value infinity. So that's how the new function g tilde is defined. So how does g tilde look like? So in terms of this expressions involving indicators, you can write it as this, that g of omega multiplied by the indicator of this set where mod of f is less equal to g, otherwise it is infinity on the set mod f greater than g. Alright, now here what is happening, observe that you have already said that this set mod of f is greater than g has zero measure, right. So that's good. And here if the function f is a limit of measurable function, so that is measurable. So measurability here is not an issue. So therefore the function g tilde that you have such defined is a measurable function. Okay, write down that argument that g function is Borel measurable. But now you observe that pointwise the function mod f is now dominated by g tilde. So on the points where mod f was dominated by g, there you have taken that value, otherwise of course the function value is dominated by value infinity. So therefore you get mod of f is less equal to g tilde. But what happens to the integration of g tilde? So again, on a set of measure 0, the value infinity does not matter. So therefore you just get back the value of integration of g on the set in the mod f less equal to g. But this indicator is of course less equal to the indicator of the whole set, therefore you can dominate the first integration by integration of g itself. G is a non-negative function, so that's not a problem. But g is given to be integrable, so therefore that is finite. Okay, so therefore integration of g tilde is non-negative, that integration is finite. Great. So therefore you observe the inequality now that integration of mod f is dominated by integration of g tilde. So this is true because mod f is dominated from above by g tilde. Therefore f is integrable. So you have proved the first part of the statement. But you would like to show that you can exchange the order of integration in the limits. Okay. Alright. So here what is happening? Look at the limit function. So here f is equal to the limit function almost everywhere. But if the limit exists, then you can also identify it with limit inferior and limit superior. So here again we are interested in integrations. So therefore in the following arguments, whenever we are explicitly writing down the equalities or inequalities involving integrations, we are not going to care about this null set. Okay, so let's look at these equalities. So integration of f, that will be equal to the integration of limit of fn's. Alright, so that's good. But limit of fn's will be equal to limit inferior of fn. So as long as you expect that integration to exist, you have that. Great. Now what you end up having is that limit inferior now comes out by an application of the Fatou's lemma, right? So limit inferior was inside, if you bring it out you get a less equal to inequality, right? But now limit inferior of the integrals is of course less equal to limit superior. So that is a standard argument involving sequences of real numbers or extended real numbers. So that you already have. Now you push the limit superior inside. Again you retain that inequality, that is by the second part of the Fatou's lemma. So limit superior now goes inside, but you still get this less equal to here. But now observe that pointwise limit superior of the functions is equal to limits of the functions, and therefore you get the equality. Okay, that's great. Okay, so therefore you have originally started off with integration of f and you have ended up with integration of f itself, but in between there has been some inequalities less equal to symbols, right? But you have obtained the left hand side term and the right hand side term which are equal. Hence Here we have used Fatou's lemma twice, but somehow you have obtained that the left hand side and the right hand side are equal. Therefore, in these inequalities you must have equalities because the left hand side and the right hand side match. So therefore, you have immediately claimed that limit inferior of the integrations of fn must match limit superior of the integrations of fn. As a consequence, you claim that limit of integrations exist. Okay, limit of integrations of fn's exists. That's the first observation. Moreover, if all the equalities hold, then you claim that integration of f, which is equal to integration of limit of fn's, it will be equal to the limit of integrations of fn. Okay, so therefore you have proved that integrations of f is equal to integration of limits of fn's, and then that will be equal to limit of the integrations of fn. So here you are allowed to exchange the order of limits and integration. So this is possible by the boundedness assumption given by the function g. Okay, so this is an important assumption that whenever you are considering general functions fn which can take arbitrary values now, but as long as the functions fn are dominated by this integrable function g, then you can exchange the limits and integrations. Okay, so that's the statement of the dominated convergence theorem, and a particular case of that will also tell you that the limit function is integrable, even if that the limit function is taken in a almost everywhere sense. Great. So we have managed to prove the dominated convergence theorem. Now we are going to see that this dominated convergence theorem is a very general result and very useful in practice. We are going to use the shorthand notation DCT to refer to this dominated convergence theorem. Now, as a consequence of this dominated convergence theorem, we are now going to make some nice statements. Okay, so continue with the setup of the dominated convergence theorem. So here you assume that fn's are converging to the function f almost everywhere, and the functions fn are dominated by a integrable function g. So mod fn's are dominated by an integrable function g. Great. Now observe that if fn's converge to f almost everywhere, then look at this sequence of functions mod of fn minus f, that will converge pointwise to 0 mu almost everywhere. Okay, therefore you do not care about the values that are occurring on that null set. Outside the null set the convergence holds, and therefore this limit will be the 0 function. Great. But observe that the function mod fn minus f can be dominated by mod of fn plus mod of f. However, you have again said that almost everywhere these things are dominated by g, right? So fn's are dominated by g and mod f is also dominated by g almost everywhere. So therefore, in an almost everywhere statement, you get a bound 2 times g for the modulus of fn minus f. Okay, but 2 times g is non-negative, 2 times g is also integrable. So as long as g is integrable, 2 times g is also integrable. Therefore, you apply the DCT to this sequence of functions now, which is mod of fn minus f, and the result will follow because you are just considering the exchange of limit and integration. So if you push the limit inside, as per the statement in this corollary, if the limit goes inside, you consider the limit function here, and the limit function is 0, so that will contribute integration to be 0. Okay, so therefore you get the statement. So this is an important consequence of the dominated convergence theorem. Now look at further results which are appearing as a special case of the dominated convergence theorem. So consider the case of probability measures, and here we are going to consider random variables. So again, remember, random variables are nothing but measurable functions as long as you have a probability measure on your domain side. Okay, great. So let's consider this theorem which appears as a special case of the dominated convergence theorem, and it's known as the bounded convergence theorem. So what do? You look at a sequence of random variables all defined on the same probability space. So here the sequence is x1, x2 and so on. Suppose you get this random variable x such that xn converges to x almost surely. So by that I mean that outside the null set the convergence holds pointwise. Now if there exists a constant k positive such that modulus of xn's are dominated by k, then you claim that all the random variables x1 x2 so on, those random variables and the limit random variable x, all of these are integrable and you can exchange expectations and limits. So first of all, expectation of x will match with expectation of limit of xn's, but then you allow the exchange to occur, that limit can come out of the expectation, and that's what you will get as the statement. And moreover, you can also claim that limit of expectation of modulus of xn minus x is 0. Alright, so how do you prove this? So again, earlier we had mentioned that if you are going to bound a random variable by a constant, a positive constant, you will immediately get the integrability. So this was discussed in note 6 earlier. But now the rest of the proof will follow from the DCT and the corollary that was discussed above. Let's make a few comments just to understand the steps. So again, as long as these xn's are bounded by this constant and xn's converge to x almost surely, you will get that x is bounded by k almost surely. Again, by note 6 as discussed earlier, x must be integrable. In particular, this argument can also be discussed through the proof of the dominated convergence theorem. So x will be integrable. So integrability is not an issue. But then if you are interested in only integrations or expectations, as in this case, the expected value of x will be matching with the expected value of limits of xn's. Okay, so that is fine because the equality holds almost surely for the x and limit of xn's. So the expectations are matching. But then by the dominated convergence theorem, you are allowed to exchange the order of integrations and limits. So expectations can be exchanged with limits in this situation. And finally, by the corollary, you get the expectation of the modulus of difference will converge to 0. Okay, that's by the corollary. So that proves it. Now here we have used a probability measure for our discussion, but this bounded convergence, this result can also be stated for the case when mu is a finite measure. So here we have taken mu to be a probability measure, but if you take mu to be a finite measure, there you cannot talk about random variables, but you can talk about measurable functions. Here if you can get that the measurable functions are dominated by some constant, then you can argue the same, that using the fact that constant functions are integrable, you will claim that if all the measurable functions are dominated by a positive constant, then the functions will be integrable. Then if the functions converge pointwise to a limit function almost everywhere sense, then you will get that the limit function is also integrable. And then finally you are allowed to exchange the order of integration and limits. Okay, so that appears as a special case of the dominated convergence theorem. But in this course we are mostly interested in exchange of order of expectation and limits, which of course appears as a particular case when you consider the probability measures and random variables. Alright, so with that observation we have finished the discussion about the dominated convergence theorem, which is a pretty general result that allows us in computation of integration of the limit function. So as long as you know the integrations of fn's, you can consider the limit of integrations of fn and obtain the integration of the limit function. Okay, so that is quite useful in practice. Alright, now in later lectures we are going to connect Riemann integration and Lebesgue integration, and using that and using the dominated convergence theorem, we are finally ready to compute integrations over the real line. Okay, so we have mentioned certain integrations with respect to the Lebesgue measure earlier, but once you have connected Riemann integration and Lebesgue integration, then by applications of DCT we are going to see some very nice results. Okay, so we stop the lecture here and we are going to continue the discussion in the next lecture.